Let's jump right in. Today's explainer is all about the high-stakes, hyper-fast world of embedded systems and real-time operating systems, RTOS. If you've ever wondered how the invisible computers running our lives actually pull it off without crashing, you are in the right place.
Think about it. How does a pacemaker or a smart car's anti-lock brakes manage hundreds of simultaneous tasks without totally locking up? In our everyday world, multitasking is just chaotic. But in an embedded system, that chaos has to be strictly mathematically controlled. A single missed calculation isn't a glitch, it's a catastrophic failure.
So here is our roadmap for untangling this. We're hitting the shared data dilemma, guarding with semaphores, the priority problem, and inter-process communication methods.
Starting with Part 1, the shared data dilemma and its concurrency challenges.
Okay, so what actually happens when multiple tasks try to edit the exact same memory at the exact same time? Well, the software world splits this into two camps, reentrant and non-reentrant functions. Think of a reentrant function like a safely shared tool. Multiple tasks can use it, no data corruption whatsoever. It can literally be interrupted mid-task and resumed later without losing a thing. Why? Because it relies entirely on local variables, stuff on the task's own stack. Take the string copy command, for example. Copies of its arguments go safely onto the local stack, keeping everything completely isolated. Non-reentrant functions, on the other hand, they're risky. They rely on shared global variables, which is basically asking for trouble.
And that trouble is data corruption. When variables or I/O registers are treated as fragile shared resources, unrestricted simultaneous access in a preemptive kernel doesn't just make corruption a possibility, it makes it an absolute guarantee. You are going to get a massive data collision. We desperately need a mechanism that enforces serialized access and mutual exclusion.
Which brings us right into Section 2, guarding with semaphores, or basically software locks.
Since we know the danger, engineers rely on software mechanisms to stop these disastrous collisions. To protect our data, we create what's called a critical section. This is a designated piece of code where exclusive access to a shared resource is 100% guaranteed. The goal here is simple but absolutely crucial. Make the operation strictly atomic. That means zero preemption, zero interruption whatsoever while that fragile data is exposed. It's kind of like sealing your most sensitive code behind a massive, impenetrable vault door.
So how do we lock that vault? With semaphores. And you've generally got two types. First, the binary semaphore. This operates on a simple 0 or 1. It grants exclusive access to a single isolated resource. Think of it like having one single key for a train track gate. Then you have the counting semaphore, which operates from 0 to n. This one manages a pool of identical resources, actively tracking how many are left. Kind of like a digital sign outside a parking lot telling you exactly how many spaces are open.
Now, let's see this in an actual workflow. By tradition, semaphore operations are called P and V. Step 1 is P, waiting to gain access to that protected resource. Once P gives you the green light, you're on to Step 2, safely executing your work inside the critical section. Finally, Step 3 is V, which releases the semaphore so the next task in line can take a turn. It's a perfectly orchestrated step-by-step dance to keep your data completely intact.
Moving to Section 3, the priority problem and scheduling headaches.
Because solving one problem always creates another, right? I want you to imagine this scenario. What happens if a low-priority task, something completely non-essential, grabs that software lock just milliseconds before a critical, life-saving, high-priority task needs it? The terrifying result is unbounded priority inversion. The low-priority task gets the lock. But then, a medium-priority task, which doesn't even need the lock, preempts it and starts running. Because this medium task is hogging the CPU, the low task can't finish and release the semaphore. So now, our critical high-priority task is stranded. It's stuck waiting indefinitely for a lock held by a task that isn't even running. Total system failure. It is literally an engineer's absolute worst nightmare.
But there's a brilliant fix for this: mutexes and priority inheritance. To stop those medium priority hijackers, the OS pulls a really clever trick. When the high-priority task requests the locked resource, the OS dynamically elevates the low-priority owner's priority to match the high-priority task. This forces the low-priority task to sprint to the finish line. Once it releases the lock, boom, it's immediately demoted back to its normal priority, and the critical task takes over. It's just a beautifully elegant, dynamic defense.
Finally, Section 4, inter-process communication methods.
So, we've locked down shared data and fixed priority scheduling. But how do tasks safely coordinate and actually talk to each other when they aren't fighting over locks? Enter inter-process communication, or IPC. There are two major styles acting as safe information highways here: shared memory, where tasks have direct access to a shared location, and message passing, where tasks send records back and forth via queues. Let's break those down.
With shared memory, two distinct components, like a CPU and an I/O device, don't actually talk directly to each other. Instead, they communicate through a very specific shared memory location over a system bus. The CPU writes to it, the I/O device reads from it. It's fast, it's direct, and it's incredibly efficient.
To put that into perspective, think about elastic buffers. Imagine a text compressor using the CPU to compress incoming text. The CPU is blazing fast, way faster than the output mechanism. So the compressed text gets safely buffered into a shared memory block. Then a hardware communication device, like a UART, reads from that buffer at its own pace and sends it out. The shared memory basically acts like a giant elastic shock absorber between the super-fast CPU and the slower output.
The second IPC style is message passing, and the most common way to do this is with a queue. A queue uses a strict first-in, first-out, or FIFO system for its messages. So instead of messing around in a shared memory block, Task A just packages up a message and drops it into the queue. Task B comes along later and pulls it out in the exact order it was dropped in. It's just a very orderly, polite handoff so nobody steps on anyone else's toes.
And that brings us to the end of today's explainer. We've seen how reentrant functions, semaphores, priority inheritance, and queues can actually bring order to the chaos of a preemptive OS. But here's what I want you to think about. As these embedded systems scale up to run billions of interconnected IoT devices and critical aerospace components, are we truly mastering concurrency? Or are we just building smarter traffic lights for a constantly growing digital highway? Makes you wonder what the next big leap in RTOS architecture is going to be. Thanks for hanging out, and I'll catch you in the next one.